Okay, we're going to do lesson 10.3, absorbing Markov chains. Since we have an absorbing state, so we know we have states in a Markov chain. You could have state A, B, C. You could have 1, 2, 3, but the circle in this given Markov chain has states 1, 2, and 3. So it says state I of the Markov chain is the absorbing state if P I equals 1, and that means like from going from some state P, or the probability of P, the probability of going, in this case, from state 2 to state 2 is 1, or from state 1 to state 1, or state 3 to state 3. And that's what we have here in the Markov chain, because I have a state 2, and it's going back to itself 1. So what it really means is entering a state and staying there, the probability is 100%, because there's nowhere else to go. Okay. You're trapped in state 2 for this one. What you need to notice is that it circles back on itself with a probability of 1. Notice that we're only going from 2 to 2. We don't have an arrow going from 2 to 1. We don't have an arrow going from 2 to 3. So that's what it means to be an absorbing state. So basically, an absorbing state is the end of it transitions from that state. So you can't go from, again, 2 to 1. You can't go from 2 to 2. You're just stuck in here. The properties of absorbing chain. A Markov chain is an absorbing chain if and only if. So these things have to happen, and there are 2 conditions. The chain has at least one absorbing state. So you can have more, but you have to have at least one of them. So in the case of the one above, we've got 2 going back to 2. Number 2, it's possible to go from a non-absorbing state to some absorbing state. So if we're looking at the example above, that just means that we can go from a non-absorbing state, which in this case would be 1, to an absorbing one, which is 2. That has to happen. Or in this case, we also can go from 3 to 2. But in other words, 2 isn't going to be just all by itself. Something has to be going into it. Example 1, absorbing Markov chain. Identify all absorbing states in the Markov chain, having the following matrices, and decide whether the Markov chain is absorbing. So for it to be absorbing, again, we have to have one absorbing state, and we have to have a non-absorbing state that goes into that absorbing state. So I actually have 2 absorbing states. I have one here because from 1 to 1, the probability of going from state 1 to state 1 is 1. So I can't get out of there. I can't go to state 2. I can't go to state 3. And I have another one as well where the probability of going from 3 to 3 is 1. Now if I look at 2 to 2, it has 0.5. So 2 to 2 is not an absorbing, state 2 is not an absorbing state. So state 1 and 3 are absorbing. And then to decide whether it's an absorbing chain, I have to see, well, do I have a state that will go, a non-absorbing state that will go into the absorbing state? And the answer, we only have one non-absorbing state, that's state 2. 2 can go into state 1. So we can go from 2 to 1 with a probability of 0.3. So that one's going to work. And we can go from 2 into 3 as well with a probability of 0.2. So we do have a non-absorbing state going into those absorbing states. So we say that we do have a Markov chain as absorbing. And for part B, again, we're looking for the same kind of thing. If I look at 1 to 1, probability of 1 to 1 is 1/2. Probability of 2 to 2 is 1, so that's an absorbing state. Probability of 3 to 3 is 1, so that's an absorbing state. And 4 to 4 is 2/3, so that is a non-absorbing state. So state 2 and 3 are absorbing. Which means basically they suck everything in there and then you can't leave. And then I need to decide, well, do I have non-absorbing states going into an absorbing state? Well, let's see, I've got my non-absorbing states are 1 and 4. 1 goes into 1. Sorry, 1 goes into 2. With a probability of 1/2. So that one's going to work. And I also see that 4 goes into 3 with a probability of 1/3. So that's also an absorbing state. Part C, again, we want to identify any of those absorbing states. So 1 to 1 is 0.6, that's non-absorbing. 2 to 2 is 1, so there we have one, state 1. Or sorry, state 2. And 3 to 3 is 0.1, so that's not absorbing. And 4 to 4 is 1, so that's also an absorbing state. Now, do I have non-absorbing states going into those absorbing states? So 1 to 2 is 0, so that doesn't go into it. 3 to 2 is 0, so that doesn't go into the absorbing state. So I'm going to check the other one. I've got 1 to 4, that doesn't work, and 2 to 4. Or excuse me, 3 to 4 is also 0. So I don't have a non-absorbing state going to an absorbing state. Cannot go from an absorbing state or from a non-absorbing state to an absorbing state. Therefore, not an absorbing Markov chain. All right, for the next example, it's kind of a long description of the problem, but basically we have player A and B and we're going to have a coin tossing. A fair coin is tossed and the player predicting the toss correctly wins $1 from the other player. So if you guess correctly, you win $1, the other player loses $1. Suppose the players have a total of $6 between them and that the game goes on until one player has no money at all. Says we're going to agree that the states of the system are the amounts of the money held by the player. So when we're looking at the different states, a person could have anywhere from 0 to $6. Okay? Those are our different states. When either state is 0 or 6 is reached, then the game is over because that means either you have no money or you have all $6, which means that the other person has no money. it says in any other state, the amount of money held by player A will increase by $1 or decrease by $1 with each of these events having probability 1/2, since we have a player. So example would be, and for all of these, this is how much money person A has, okay? So just an example, if I'm in state 3, I have $3, and there's a 1/2 chance of changing to state 2, and a 1/2 chance changing to state 4. And it's state 2 because I could lose $1, which would give me $2, or I could gain $1, which would put me in state 4. So that's why I'm only in 2 or 4 as opposed to the others. The probability from state 3 to any other state is 0. And we're going to use this information. We have a 7x7 transition matrix. So what we want to do really is look at what in the long term is going to happen to this. And there's a really quick way of estimating what's going to happen at the end of this game, or the probabilities, depending on how much money you have at the time, where you're going to end up. So what we're going to do is we're going to take our P matrix there, and we're going to go to a really high power. We're going to take it to the 99th power. So we're going to put that in our calculator and go to the 99th power. And here's our outcome. This is what it's going to look like. Approximately. So what we end up with is basically a bunch of numbers for column 0 and column 6, because at the end, if you just keep playing, there's ultimately going to be an ending, and the game is going to end with either having no money or having all of the money. That's kind of how the game works. So it says the probability of starting with 0 and ending with 0 would be 0.1. Probability of starting with $1 and ending with 0 would be 0.8, and winning all the money would be 0.2, and so forth. So you can see that as we go through the game multiple times, 99 times, that we're going to end up either winning or losing. There's not going to be any reason for that. So that's how we do an estimation. So we're going to just try that out here with the third example. It says we've got estimate the long-term trend for the following transition matrix. All you're going to do is take this little guy, again, take him to the high power. I usually take it to the 99th power. Okay. When you do that, our results are going to be approximately 0, 0.3, 0.7. 0, 1, 0, 0, 0, 1. So we still have those absorbing states that you can see. State 2 and state 3 are absorbing states. So, but this is our final outcome. So if we did this multiple times, basically everything would end up looking like this. Anything past the 99th power is pretty much all going to look the same. So kind of level it out. So the example suggests the following properties of absorbing Markov chains, which can be verified using more advanced methods. So again, those were estimates, so we can do a little bit better than that. We can get a little more precise. The first thing is, regardless of the original state of the absorbing Markov chain, in a finite number of steps, the chain will enter an absorbing state and then stay there. So basically, we're getting closer and closer and closer to a matrix that will look the same. At some point, it will just start to all look the same. Number two, the powers of the transition matrix get closer and closer to some particular matrix. Kind of reiterating what happened in 1. And 3, the long-term trend depends on the initial state. Changing the initial state can change the final result. And that's a little bit different from a regular Markov chain as opposed to the absorbing one. In a regular Markov chain, the final result is always independent of the original. Okay, now we're going to get a little more in depth. And this next example here is a little bit longer. And it looks like our coin game that we play. Okay? So it's that still that same problem. Going back to example 2. It says we're going to write the matrix from example 2 so that the rows and columns of the absorbing states come first. So remember, the absorbing states were 0 and 6. And so I'm going to write those rows in. And I'm going to put those first. And then just in the same order that they come in, I'm going to put 1, 2, 3, 4, and 5 as the rest of my rows. So we're going to write it that way first. And then what happens is, and we also want to put our columns. We can see the columns are that way. So we got 0 and 6 there in our columns as well. And then all of our non-absorbing states. So that we make what's called an identity matrix there in the top left-hand corner, that 1, 0, 0, 1. So we'll mark that off. And we create 4 different sections then of our matrix, which is the example of what we have right here, where it says P is equal to, in the upper left-hand corner, we have I, which is our identity matrix. In the upper right-hand corner, we have O, which is our 0 matrix. You can see all the zeros there. In the bottom left, we have R. And in the bottom right, we have Q. So we're going to identify those different parts so that we have 4 different little matrices. The fundamental matrix for an absorbing Markov chain is defined as F, and we're going to use this equation right here. So F equals I, which is our identity matrix, that's the part in the upper left-hand corner, minus Q, which is the part in the lower right-hand corner. And then we're going to take it to the negative first power, which is the inverse. The fundamental matrix gives the expected values before absorption occurs. So before we get trapped in something, it's going to give us, right before that happens, that stuff happens, we're going to find out what F is. So I'm going to use the data from the top there, and we're going to get a value for F, which is our matrix before this thing absorbs. So we have to identify our I. In this case was the matrix is 1, 0, 0, 1 minus Q. we subtract is that we have to have matrices that are the same size. And that's not happening here for us. So we're going to resize our identity matrix so that it's the same size as Q. Our Q is a 5 by 5, so we want our identity to be a 5 by 5. So I'm going to rewrite that. An identity matrix, it's just going to have a diagonal filled with 1, so the rest are going to be zeros. So now I have a 5 by 5 minus Q. So what I would do is, in my calculator, I would make the identity matrix, matrix A, and I would make Q, matrix B. And then you're going to take A minus B, get that matrix, and then put it to the negative 1 power. Make sure that you do this to the negative first power, and that's going to give me F. F is equal to the big one, not fractions. So basically, these are the probabilities before this thing starts to do what's called absorbing, where we get stuck in one particular state. So that means probably the next toss of the coin is going to put us in the absorbing state. And then to find the actual probability of going from a non-absorbing state to an absorbing state, that's what we're doing when we take our F times our R. So we already have F, it's over here. So I'm going to say this is matrix F, and then I'm going to multiply that times R. R looks like 1/2, 0. And I'm going to multiply that out. This is a long one. So we get what that tells me is my absorbing states are 0 and 6. So this tells me, for example, if I start out, if I'm in state 2, so I have $2, the probability of ending with $0 going into the absorbing state is 2/3. And the probability of winning, getting $6, is 1/3 at that point. If I get to the point where I have $5, the probability of losing that game at that point is 1/6, and the probability of winning is 5/6. So it tells me the different probabilities based on where I am at currently. Okay, some properties of absorbing change. It says regardless of the initial state and a finite number of steps, the chain will enter an absorbing state and stay there. So after it may be the 20th game, it may be the 99. We don't know, but at some point it's going to get to where we get to a state that stops. It stays there, we can get out. The powers of the transition matrix get closer and closer to some particular matrix. The long-term trend depends on the initial state, so whatever we start with is going to affect what happens in the end. Number 4, P, which is our transition matrix for an absorbing Markov chain. What we want to do is rearrange so that we have this one represents our absorbing states. And then we can take the parts from P. We rearrange our values and find F, which is the fundamental matrix. And then at that point, once we get F, you're going to see F times R, and that's going to be the probability that a particular non-absorbing state will enter an absorbing state. Basically, what's going to be my outcome of the game if I'm at state 3 or state 4 and so on. Okay, example 4, we're going to do this, the same kind of thing with this. It's a little bit smaller problem. So we want to find F times R. To find F times R, I'm going to first rearrange okay. So I'm going to take my absorbing states. My absorbing states are 2 and 3. And so I'm going to put those as my rows and my columns first. So I've got 2, 3. One's going to be the last one on the row and the last one on the column. And then I'm going to put my entries in there. So for 2, 2 was 1. For 2, 3 was 0, and 2, 1 was also 0. For 3, 2, I have 0. For 3, 3, I have 1, and 3, 1 is also 0. 1, 2 is 0.2. 1, 3 is 0.5, and 1, 1 is 0.3. And now where my absorbing states are, that's where I'm going to draw my line. So that this is I, and this is O, and R, and Q. Okay. So that's the first step. The second step is to figure out what F is. F is equal to your identity matrix, which is in the upper left-hand corner, minus Q, and then to the negative first. Now remember that the size of I has to match Q, so we could actually do that ahead of time. We know that Q is 0.3, so there's only one value in there. So an identity matrix for a 1 by 1 is just going to be 1 itself. So that's 0.7 to the negative 1, which is 10 seconds. So that's F. And then step 3 is going to be to tell me, well, what is F times R then? F times R is 10 sevenths times R, which is 0.2 and 0.5. So it's a little scalar multiplication. That's going to give me 2 sevenths and 5 sevenths. So our absorbing chains were, our absorbing states were 2 and 3, and our non-absorbing state was 1. So to go from 1 to 2 is 2 sevenths, and from 1 to 3 is 5 sevenths. So that's the exact answer as opposed to the an approximation, which is what we did in, I believe, example 1.